Math 1343, Week 8, Video 9, Expected Values for a Test for Association. As I mentioned in the previous video, the general flow for a test for association is kind of like the flow for a goodness of fit test. We have some claim about a population, we have some observed values, we calculate what's expected, and then we come up with a measurement for the difference between what we observed versus what we expected, call that the test statistic, and then do our hypothesis test. For a test for association, we're going to do pretty much the same thing. So in order to do that, we have to calculate our expected values based on our observed values. Oh, by the way, I forgot to mention in the previous video that a table like this that separates data based on two classifications, in this case gender and type of degree, is called a contingency table. Speaking of which, here's the contingency table from the previous video, as well as the hypotheses that we're eventually going to use in our hypothesis test. So, based on what we observe, how would we calculate what we should expect? Well, that calculation is based on the totals for each row and column in the observed values. For example, and shame on me for not calculating these totals in advance, but that's not too hard to figure out. When we filtered our observed data into this contingency table, we can recover how many males there were by simply adding up the first column. 1,340 plus 4,110 plus 17,383 is equal to 22,833. 22,833. So that's how many males we observed. And for the females, 2,899 plus 5,067 plus 17,161 is 25,127. But if we also take the total for the number of each type of degree and write that to the right of the contingency table, get the feeling I'll need to separate these two. The total number of bachelor's degree recipients was 1,340 plus 2,899, which is 4,239. The total number of master's degree recipients was 4,110 plus 5,067, which is 9,177. And the total number of doctoral degree recipients is 17,383 plus 17,161, which is 34,544. Now, we can check that our sums are probably correct by taking a grand total in both directions. If we add up the total number of males and females, it should equal the total number of bachelor's, master's, and doctorate recipients. So let's check that. 22,838 plus 25,127 is equal to 47,965. Put my commas up there. And if we add up the total number of degree recipients, this column, 4,239 plus 9,177 plus 34,544 is equal to something different, 47,960. So I have a discrepancy, and now I need to find it. I know what my discrepancy is. I mistyped this number. When I typed it, I typed 838 instead of 833, and I might have said that. So let's try adding up the bottom row again. 22,833 plus 25,127 is 47,960. But the reason I added up the final row and the final column wasn't just to make sure that I didn't make an arithmetic mistake. And I'm kind of glad I did, because I had when I mistyped this number. But I'm going to need not only this total, but all these totals in calculating the expected values. So let's go ahead and title this the total and the total. Now, how do we calculate the expected values? Well, remember, what we expect is based on the null hypothesis. that there is not an association between gender and type, meaning that any comparable proportion should be equal. But proportions are always out of a total. So to calculate the expected values, the first thing we would do is import all totals to the EV contingency table. EV meaning expected value. So we're going to take all the totals that we have and move them over here. Total number of males, 22,833. Total number of females, 25,127. Total number of bachelor's degree recipients, 4,239. Total number of master's degree recipients, 9,177. And the total number of doctorate degree recipients, 34,544. And the grand total in either direction was 47,960. Now, what do these totals represent? These totals represent ignoring a category. For example, these totals over here ignore who is male and female. 4,239 people received bachelor's degrees. Were they male or female? Don't know. Didn't make note. I just counted how many received bachelor's degrees. Or this represents the total number of males who received degrees. What type of degree? I don't know. I just wrote down their gender. So I forgot how many received each. So our expected values are built off of the observations based on ignoring one of the categories. If we ignore gender, then here's our degree totals. And if we ignore degree type, then here's our gender totals. Now, how do we use this to calculate the expected values? I'll tell you right now, we're going to figure out how to come up with one expected value, turn it into a formula, and then use it to calculate the others. Let's start with the number of males who received a bachelor's degree. The premise behind the expected values, and specifically the null hypothesis, is that the proportion should be the same regardless of whether or not you look at gender. So for example, notice that we have 4,239 bachelor degrees out of the total of 47,960 degrees conferred, whether bachelor's, master's, or doctorate. So we can calculate a proportion out of this by simply making a fraction. This divided by this would tell us what percent of the degrees were bachelor's degrees. Now, if gender didn't matter, then it should be the same proportion for males and the same proportion for females. In other words, if we were to try to figure out what number goes here, let's just put a question mark there for a second. If we were to try to figure out what number goes here, then the proportion of males who receive bachelor's degrees, in other words, this number divided by the total number of males, should be the same fraction as if it were the total number of bachelor's degree out of the total number of degrees if we ignore gender altogether. If gender didn't matter, those proportions should be the same. So what that means is, when we take whatever number goes where the question mark is and divide it by the total number of males, if there were truly no association, then this proportion should be equal to this one over here. 4,239 divided by 47,960. And if we did just a little bit of algebra and multiplied both sides by the denominator over here, then it would show up on top of this fraction. And that would give us a formula for calculating the missing value, the missing expected value for the number of males who receive bachelor's degrees. What's this equal to? Well, that's just a calculator thing, but I want to focus a little bit more on how we built that, because that's where our formula is going to come from. To calculate the expected value of the number of males who receive bachelor's degrees, in other words, to calculate the expected value of this cell, what we observed was this, but what we should have expected for perfect proportionality, this expected value is the product of the row total that it came from, 4,239, and the column total that it came from, 22,833, divided by the grand total of everything. So in other words, this cell's expected value is the product of its row total and its column total divided by the grand total. Let's go ahead and figure that out, and then we'll write it down as a formula. And for the sake of not having too many digits in here, I'm just going to round to the nearest whole number. In general, I like 4 decimal places, but in a problem like this, that can get out of control. 4,239 times 22,833 divided by 47,960 equals, to the nearest whole number, this is about 2018. So if we had perfect proportionality, or at least as close as we can get with whole numbers, then we would have expected 2018 males to receive bachelor's degrees, making the proportion of males who receive bachelor's degrees the same as the proportion of all people who receive bachelor's degrees. But what really happened here is we built a formula. So without further ado, we'll fill in step 2 here in just a second. In fact, we'll fill it in right now. For each cell, the expected value, really not going to write it here, I'll try. The expected value is the following formula. It is the row total times the column total, if I can spell total, divided by the grand total, but honestly this is our sample size. I'm going to write grand total, but most books would say the sample size. Out of a sample of 47,960 students, we saw all that, but we'll say grand total. I'm going to write that up here. Expected value equals, we'll just say row times column divided by total. That's a little more succinct. And now that we've figured out how to calculate the expected value in an individual cell, we can now calculate the expected values for the remaining cells. For example, for the number of females who receive bachelor's degree, we would multiply the total number of bachelor degree recipients, in other words, the total of this row, 4,239, times the total number of females, this row, this column, 25,127, and then divided by the grand total, which is always going to be the same, 47,960. And let's see what that is to the nearest whole number. 4,239 times 25,127 divided by 47,960 is not the correct answer because I hit times instead of times divide. Luckily I can edit that really easily. There we go. So to the nearest whole number, this is 2,221. And so if we had perfect proportionality, we would expect 2,221 females in that cell. And we can do the same thing for the rest of them. I'm not going to write down every multiplication and division problem that I'm going to do. I'm simply going to call out what I'm going to do. But in practice, I would write them down, especially if you're doing it on a test, because if you write it down correctly and put it in a calculator incorrectly, you can get partial credit for the setup. All right, so let's move to males who receive master's degree. We multiply the row total times the column total and divide it by the grand total. So for this cell here, let's go back to red for a second. So for this cell here, the row total is 9,177 times the column total, 22,833, divided by the grand total, 47,960. To the nearest whole number is 4,369. 4,369, which is a little bit more than what we observed. Actually, it's a lot more. When we calculate the test statistic in the next video, we'll see how impactful that is. For the females who receive master's degree expected value, we're going to multiply the row total, 9,177, we're right here, times the column total, 25,127, divided by the grand total, divided by 47,960, and we get to the nearest whole number, 4,808. 4,808. And then finally, for the males who receive doctorates, the expected value would be the row total, so 34,544, times the column total, 22,833, divided by the grand total, 47,960, and to the nearest whole number, that is 16,446. And finally, for the females who receive doctorates, the expected value would be the row total, 34,544, times the column total, 25,127, divided by the grand total, 47,960, and to the nearest whole number, we would expect 18,098. All right, so these are our expected values. Now, what do these expected values do? Number one, they establish perfect proportionality, well, to the nearest whole number values. So for example, if I figured out what percent of bachelor's degrees were male, then it would be the same as the percent of bachelor's degrees that were master's. Excuse me, that's not correct. If I figured out the percent of bachelor's degrees that were male, actually that is correct. The proportion of bachelor's degrees that are male is the same as the proportion of master's degrees that are male, which is the same as the proportion of doctorate degrees that are male, which is the same as the proportion of males out of the total. In other words, any proportion that I could form should be the same going across and the same going down. Also, it preserves all the sums. Check the sum of these, you'll get the same total. Check the sum of these, check the sum of these, check the sum of each column. Now, because we rounded, there's a possibility they could be off by one, but I'm pretty sure all of these are exact. Just a real quick glance tells me that that is the case. I didn't add them all, I just checked the ones digits. So it seems like a lot of work to calculate the expected values, but really it's just multiply and divide. For each cell, multiply the row total times the column total and divide it by the grand total, and that's your expected value. So what do we do with these? Well, we're going to calculate a test statistic in the next video.